Hello. So here's part 3 of our lab on discrete distributions. So we've covered the Bernoulli distribution, the geometric, and now we're going to talk about the binomial distribution. So what is a binomial? Binomial describes the probability of getting a certain number of successes out of a fixed number of repeated Bernoulli trials. So we got a fixed number of people, a fixed number of trials. And so here we have a formula for what this probability is. If P is the probability of success for a Bernoulli trial, we're going to observe exactly K successes in N. What's that probability? Here it's this formula. If you want to see it pop up, sometimes it doesn't. You can delete the $sign and put it again, and it should pop up. So this is a formula that is a mess to mess with. I don't recommend trying to type this in any way. Instead, we're going to use the binom. This function here will do everything we need as long as we put in the answer, the parts of our question right. So let's consider this example. What are the chance? We want to consider the probability of meeting a deductible is 30% as before. And say we sample 8 people. I got a small company, 8 people in it. What's the chance that exactly 3 of them meet their deductible? So we're going to set it up like this. Success will be meeting one's deductible. So that probability will be 0.3. N will be the total number of people or trials that we're looking at, and K will be the number of successes. So K is 3. This is where we run our function. K is 3 here. We run it, and it tells us the probability. It's got a 25% chance of this situation occurring. Okay, we could also consider this, all these binomial distribution problems you can consider from either approach. We could also look at the same thing. What if 5 do not meet their deductible? That's the same thing as 3 out of 8 meeting their deductible. So let's do the problem this way and see if we get the same thing. So success is not meeting your deductible. That's 0.7. If fixed number of trials is still 8, but we're looking at 5 people not meeting their deductible. Again, that's the same as 3 meeting their deductible. We will get the exact same solution. So if you're ever sure in one of these problems which way to define success, it doesn't matter as long as you identify the correct numbers given how you characterize success or failure. So here's a cool thing we can look at. If I plot, I'm going to actually type it like this. K is 0, 0:8, and I'll make P 0.3. So I'm saying I'm going to make X an array of K. This is 0 up to 8. N is the size, probability is P. This is a nice format for how we could do a bar plot. And so X is going to, if I run this here, it'll give me, I have to run all this together first. Redefine my N and my K. If I run this now with my K as that set of numbers, it gives me the probability for 0 people having the deductible, 1, 2, 3, 4, 5, 6, 7, 8. So I can plot this as a bar plot and see very nicely what this distribution looks like. So we can see this is the probability of K people meeting their deductible out of 8. So what is the most likely outcome of this? Looks like from this bar plot, we can see that 2 has the highest probability of occurring. So we could say 2 people. It's most likely. All right, so now let's look at the probability that exactly 2 out of 8 meet the deductible. From here, it looks like it's somewhere like around 0.3, but to exactly calculate it, to properly calculate it, we're going to copy this bit of code here. And this is excellent. You don't have to memorize this. Just make sure you understand how to use this code for later problems. So if I'm looking at meeting their deductible, probability of meeting the deductible would be 0.3. I just noticed there's an error above here. This should be probability of not meeting. Let me calculate that out. Caught myself. So again, the blue is just a comment. It doesn't do anything. It's just telling me what I'm thinking. So this helps me put my answers in right. So the probability of meeting a deductible, we're going to call that success. That means we look at 2 out of 8 successes. And so that's all set up right. Now I can run it. It gives me the probability of exactly 2 out of 8. Well, what about this next one here? It's the probability that all 8 out of 8 don't meet the deductible. I don't know. I'm going to set this up as don't being 0.7, probability of not meeting your deductible. And that way I can just say 8 out of 8. So about 5%. So what about number 15 says, if we randomly sample 20 cases, instead of 8, we got 20, what's the most likely number of cases we would expect to see from our distribution? So how we could look at this is by looking at the distribution of all cases, which we did very nicely here in this bar plot. So I'm just going to copy this whole bar plot. I'll put it here for number, what's it, 15. So this bar plot that we made, I'm just going to modify my numbers now. We're looking at 20 people instead of 8. So I want to do k equals 0 up to 20. I want to get all these possible outcomes. That'll give me k equals 1, k equals 2, k equals 3. I'll plug the 20. So same probability of success. And so now this is set up nicely I modified it earlier to do exactly what I want. I have my k in here, the number of successes, and fixed number of trials. P is my probability of success. And so to plot this now, I'm just going to change my n to 20 so that my title is accurate. So, there we go. There's my binomial distribution for 20 people. So what is the most likely number off that chart? Let you guys answer that for question 15. What is the most likely number of cases based off this distribution? Okay, so that's calculation side of doing the binomial distribution. Get some practice with that. The other angle we need to take when we use the binomial distribution is there are some assumptions. And this is also a really good thing to just keep in your notes for the future. When we're using the binomial distribution, there's a fixed number of trials. Instead of the geometric, where we're looking at any number of trials until we achieve our first success. Here we're saying, no, there's a specific number of people we're selecting. And in each trial, the outcome is a success or a failure. And the probability of success must be the same for each trial. It shouldn't change from trial to trial. So that will happen if we're randomly sampling people from a big enough population. If we have a small population, this condition might not be met. And the trials must be independent. So let's test it with this situation. Suppose the probability of someone developing lung cancer in their lifetime is about 30%. That's actually accurate. It's about 30%. The chance of someone who smokes developing lung cancer. So that's not good odds if you're smoking. So suppose I have 4 friends, all of which who smoke. Are the conditions for modeling the binomial distribution satisfied? So let's check. Is it fixed number of trials? Yes, we have 4 people, fixed. Is each trial success or failure? Looks like either person gets lung cancer in their lifetime or not, so yes. What about the probability of success? Is the probability of success the same for each trial? Well, if they're all smokers, yeah, the probability of getting success is the same. So, same probability of success. This is satisfied as well. What about the last one? Independence. Independence. Notice you have 4 friends. Your 4 friends are likely to share other habits, meaning they are not independent trials. You would pick someone from a potentially biased sample. So we do not have independence in this sample. So we can't fully assuredly use the binomial distribution to model this. There's probably going to be more going on with this case. But sometimes in statistics, what we do is we admit, hey, there's one of these conditions it's not met. Now we can proceed with our analysis saying, hey, we've talked about it, we've covered our bases. Now, if it were to be the case that they're independent, if we're able to make that assumption, what would be the probability? So let's look at that. What's the probability that of your 4 friends getting lung cancer, exactly 1 gets lung cancer? So of those 4 friends, I'd like you to try this yourself. Of course, you could pause the video, try to do it yourself. Take this code from before, which calculated the probability, and see if you can modify it correctly. All right, so once you've solved it yourself, now you can come back and check. Let's see, the probability of success of getting lung cancer. I'm gonna say the probability of smoker getting lung cancer. This helps me understand what I'm looking at. It was 30%. And we're looking at N is 4 friends. And number of people getting lung cancer is just 1. Chance that exactly 1 person gets lung cancer. So 41% chance. Ooh, it's a little scary. That means of my friends, got a 40% chance that one of them's getting lung cancer. Well, maybe I'm still hoping for something better. What's the chance that no one gets lung cancer? Oops, I'll let you pause this and try to get this one figured out too. All right, so once you got this, you'll notice the only part that changes is the number of successes. We got 0 friends getting lung cancer. So we're looking at a 24% chance, about a 1 in 4%, 1 in 4 chance. Okay, so now if we want to do this last part, what is the probability that that 1 or more will get lung cancer? I'll do 2 ways, whatever makes the most sense. 1 or more would be not 0%, right? 0 was 24% chance. So 1 or more would be the complement of that. It's a pretty clever way to answer this one. Since B and, oh, this should say C, huh? Interesting. Since B and C are complementary, they are going to add up to 1. So we can use that rule. The other way you could do it, I actually kind of like this way because it makes more sense to me, is if I have 4 friends, I want to know the chance of 1 or more developing lung cancer. I could say 1 colon 4. 1, 2, 3, or 4 is the K that I'm looking at. I'm looking at 1, 2, 3, 4, and I could do D binom of those. These are all my probabilities for that. So these are the 4 outcomes that could occur if 1 or more. So I just need to add them together since they're mutually exclusive events, and we get the same answer. Very good. So it looks like you just have 1 problem to practice doing some of the same calculations, and of course a pretty cool extra credit assignment. So again, to delete the extra credit, you just go like, to unlock the extra credit, you delete what's called HTML comment, and then you can work on it if you choose to do so. All right, we'll see you in class or in the next lab video.